This video is on bases other than E and applications. When we did derivatives of exponential functions, and there were some problems on some of your homeworks where the base was like 2 to the x or 5 to the x, and we didn't really discuss those. Well, now we're going to discuss them. What I do want you to remember is anything to the 0 power is 1. Dividing when the bases are the same means you subtract your exponents. When you multiply with the same base, you add your exponents, and if you have a power to a power, you multiply them. In addition to this, I want you to remember how to change from an exponential function into a log function. For these first set of examples, I will do A, C, E, and G, and I will give you the solutions for B, D, F, and H. However, you will need to figure out how to solve those. So for this, there's no calculus involved yet. This is just solving for x. Well, this is 32, and this is 2 to the something. So we're going to have to make sure that they have the same base. Well, 2 to the x minus 3, we're not going to change. But 2 to the 5th power is the same thing as 32. Our bases are now the same, so we can cancel them out and just solve our exponents. So x minus 3 is equal to 5, so our x is equal to 8. Same concept on part C. We don't change them into a base of 8. It'll still be to a base of 2 to the 3rd, x minus 3, equal to 2 to the 4th of x plus 2. Since we have a power on the inside and something on the outside, we multiply them, cancel our bases. 3x minus 3 equals 4x plus 8. Solving for x, and we get x is equal to negative 17. Now for part E and G, they're written in log form, we need to write them in exponential form. So we would get 4 to the x is equal to 1024. 4 to the x is equal to 4 to the 5th power. Our bases are now the same, so x is equal to 5. Here we would get 9 to the x is equal to 1, and we know that anything to the 0 power is 1, which would then make x here to be 0. Now the solutions for these are x is equal to 2, x is equal to 11 over 7, x is equal to 1/3, and x is equal to 8. Make sure that you try these because they might be on your test coming back from Thanksgiving break. On this next portion, we have the definition of a log function to a base of a. But really, essentially, we're going to be looking at this portion right here, which is showing you how to find the derivative for bases other than e. And this is what we'll be using for the next set of examples. So on example 2, our derivative here would be ln of a, and a is our base, which is 3, times our function itself. And we are done. On part B, first we find u, kind of like our u substitution, which is 3x. Take the derivative of that, which would be 3. So our derivative here would be ln of 4 times our function times the derivative of our exponent, and there's our solution. Same concept on part C. U is equal to x squared. Our du would be 2x. So our derivative would be ln of 5 times our function times the derivative of our function. Do not multiply the 5 and the 2x because they don't have the same exponents. We would just leave our answer as is. Part D, u is equal to 3 minus x squared. Du is equal to negative 2x. So y prime would be ln of 5 times our function times our derivative of our exponent. For example 3, we will be using this rule right here, which states u prime over ln of a times u, and this is how we're going to find the derivatives of log functions. So for example, a, the derivative would be the derivative of, well, u is x, and the derivative of x is 1, so we have 1 over ln of 5 times x, which was our u, and that's our derivative. U here is sine of x, du would be cos of x, so our derivative here would be cos x over ln of 3 times sine of x. For this one, we don't have a value of a. However, when you're not given a value for a, common logs are base of 10. So here, our u is x plus 3 to the x. The derivative of this would be 1 plus, using our previous example, ln of 3 times our function. So then we have 1 plus ln of 3 times our function over ln of 10 times x plus 3 to the x. For example D, I have set u to be 2x plus 1 to the 1/3. I found the derivative, which is chain rule, so it would simplify to 2/3, 2x plus 1 to the 2/3 on the bottom. So the derivative would be, I'm going to write it as two fractions, 2/3 to the 2x plus 1 to the 2/3 times 1 over ln of 2 times 2x plus 1 to the 1/3. I can combine the 2x plus 1 to the 2/3 with the 2x plus 1 to the 1/3, because those bases are the same. I add my exponents, which would then simplify to 2 over 3 ln of 2 times 2x plus 1. Example 4, find an equation of a tangent line of f of x equals 6 to the x, where x is equal to 2. Well, before we can do anything else, we have to find our y value, which in this case, substituting in 2 for x gives us a y value of 36. So now we find the derivative of the function. Since this is a base other than e, it becomes ln of 6 times our function itself. So then the derivative at 2 would be 36 ln of 6. We could simplify it, but we won't. So to write the equation of a tangent line, it would be y minus 36 equals 36 ln of 6, parentheses, x minus 2. And we would be done. For this next example, we're asked to find the weight of the culture after 0 hours, 2 hours, and 8 hours, and then they want us to find what is the limit as t is approaching infinity. Well, I've set up the first one, and when we simplify this, it gives us 1 ounce. If we do the same for 2 hours, this then approximates 1.1455 ounces. If we do the same for 8 hours, then this approximates 1.2843 ounces. And if we were to continue, the limit of the function as t is approaching infinity is actually approaching the numerator value, because it won't get any bigger than that, which in this example is approximating 1.3. So to answer the question, what is the limit of the weight of the culture, is 1.3 ounces. You can prove this by going through more sets of hours if you don't quite understand what's going on. But this is it. This is a video on bases other than E, and I hope it has helped you, and I shall see you soon.